Hi everyone, welcome back. So let's talk a little bit about special notation, where I know there's a lot of textbook and practice problems. They use to express it instead of the one we have derived. So basically, we have finished the series basically. So we say we can exponentiate a matrix, and we can solve for the own eigenvectors, eigenvalues, and we can exponentiate it. So we can express our values, okay? So let's say you get, before we start, right, comment on various different notation. So you notice something interesting, right? If you recall from calculus or differential equation class, if you assign a problem like this, dy over dx equals 6x, how will you solve it? You get dy I'm sorry, 6y. So dy over y equal to 6dx, and if you integrate both sides, dy y equal to integral 6dx, so you get ln y equal to 6x plus c. So you get y, if you e both sides, equals e to the power 6x times e to the power c, which is, or in other words, 6x times y0. Okay? So similarly, you can do the same for matrix. Recall we can reduce a matrix. Let's say ddt of matrix M equal matrix A times matrix M. Oh, I'm sorry. It should be a vectors. Let's say you can reduce to this. And so you should get your vector v is equal to e to the power of a times v0. Right? However, they write like this. Okay. However, some textbook like it is, some textbook right like this. They write v equal to summation of c is a constant, e to the lambda it, where lambda is an eigenvalues, times vi. Okay, I will, in this case, today video, I will explain to you why that happened. Okay, so in details. So basically, let's set up an example. Let's say, we'll show A this B. I will show you why A equal B. So, for example, let's say you have a system. Let's say you have a system like x dot equal to ax. Okay, and if you don't know what is x dot is just basically the first derivative of x, but this is a more common notation. It's reduce the writing. So you see expressed like this more, where your x is gonna be your concentration of particle or compound A as a function of time, and your concentration of compound B as a function of time. So your x dot gonna be the derivative of that with respect to time, and also the derivative of concentration B with respect to time. Or in other words, this is a derivative vector. Okay. So let's say lambda is going to be our eigenvalue of V. It's going to be our eigenvectors. And so you must recall what is previously, I think it's part 2 or part 3, we say P is a collection of eigenvectors. So P will look something like this. V1, V2, all the way to Vn. Okay. So I'm going to assume there is n eigenvalues. Okay, I'm going to assume there's n eigenvalue. So what would happen? So you have a system, you say x dot equal ax, right? So your x, which is the complete vector as function of t, should be equal to e to the power of a. Okay, so it will equal to p e to the power of d. D is diagonal matrix. P to the negative 1. Oh, sorry, this is super x0. So this is exactly like what we did previously. So dy over dx equals x6y. So you get y equals e to the power 6x times y0, y at t equals 0. So the same idea can be applied to matrix, okay? So e to the power of a, we have spent a whole series to show that e to the power of a can be decomposed to this times x at t equals 0. x0 means x at t equals 0. Okay, excellent. So let's go ahead and group it because let's use the property of matrix associativity. So you can say equal to p e to the power d, and then you can group these p negative 1 x0 based on the matrix associativity. Okay, now let's go ahead and expand it out. The first one, p times e to the power d, what it's going to look like. So recall now, p is going to be collection of column vector v1, v2, all the way to vn. And then what's ed is going to look like? Ed is just, we already showed that, if you recall, e to the power of d, it's just basically the matrix full of exponential of the diagonal values. So this way we can say this is the collection of e to the power of lambda t1, that is 0, and then you have e to the power of lambda 2, 0, and then you have on the way to 0, 0, e to the power of lambda n t. Okay, because remember, it is the function of t. Okay, wonderful. So for our next one, p to the negative 1, I don't know what it looks like, but I'm pretty sure it's n times n. Oh, I haven't checked the range for you. Okay, so p is n times n, all this square matrix, and we say it's have n component, right? So we assume there's n eigenvalues. So there's n eigenvectors, so you have n. So p is going to be an n by n. So similarly, p times p inverse is n by n as well. This n by n as well, and x0 is just a vector, so n times 1. So all this you group together, you get an n times 1, which is an n times 1 matrix or a column vector. Okay, so it's good. So x0, what's x0 look like? x0 gonna be, remember, x0 is gonna be our concentration at t equals 0, right? So it's gonna be our c, I'm gonna write out c1 at t equals 0, c2 t equals 0, to in a way to cn at t equals 0. Okay, let's go ahead and break this out a little bit. So, if you recall to Blue One Pro matrix multiplication video, you can say on the left hand side we apply each v1, v2 to each of the column vectors. So we apply v1 to e lambda 1 t 0 all the way to 0, and then you do the same for v2, apply v2 0 lambda 2 t 0 all the way to vn. Okay, so basically each of the column vectors will be transformed by this operation, by the left operation, by the L operation. Okay, how about these two? So basically you have to, there's something interesting you can observe here. C1 0, C and C2 0, sorry. And Cn 0, all this is a number, right? P to the power of -1 is also like a constant because it doesn't have a t in it. So this is constant, this is constant, right? Because it doesn't have a t in it. So what you can say is that this basically this is an n times 1 matrix, by the way. So you can say all this is just basically an n by 1 matrix or a column vector with constant. So let's call it constant C1, C2 all the way to Cn. Okay, because you times two matrix together with a constant both, you just all you can care about is the final dimension, which is an n by 1 dimension, and it's just a constant. Okay, so wonderful. So what is the left hand side equal to? The left hand side, if you notice, is very simple. So this term right here, okay, it will become what? It will become v1 lambda 1. Do you agree with me? Because on this right here, what will be equal to? It could be v1 e lambda 1 t plus v1 times 0 plus on the way to v1 times 0, right? And all these right here is going to be v2 times 0 plus v2 times e lambda 2t on the way. You see what I'm saying? So basically you can get this one, you can get e lambda 1 t v1. This one you can get e lambda 2t v2, and on the way to e lambda n t vn. Okay, because basically what you did is once you apply the matrix, you just times and add them. Okay, so and this one just retain it, so C1 C2 all the way to Cn. And if you times them once more time, you apply each of these to this, you should get you apply these terms to this, you should get e lambda 1 t v1 c1 plus e lambda 2 t v2 c2 plus on the way to e lambda n t vn cn. Okay, or in other words, this is the summation I equal 1 to n of e to I lambda I t v I c I. Okay, where vi is just the corresponding eigenvectors, and lambda I is just the corresponding eigenvalues. Okay, so I hope this helped. I know it's kind of a little bit tight, but just remember when you times, there's intuition in everything. So when you times them together, write a matrix operation completely so you can understand. So I hope this video is helpful for you. You can write both ways. As you can see that both way will lead to the same result. And we use the very same idea from basic calculus to get us here. So I appreciate everyone for your attention, and I wish you have an amazing and meaningful life. Thank you so much.